Hello, everybody. It's find the seats. So it's great to open up another session of our Physics and Applied Physics Colloquium. I'm Ben Love, and I have the distinct pleasure of introducing Adam Kaufman, who is one of the guiding lights, I would say, in the new generation of quantum physicists. And it's an absolute pleasure to have him here at Stanford and hang out with us for most of this week. Adam, really specializes in kind of gaining this unprecedented control of quantum particles, both for fundamental physics and actually for other things like clocks, sensing, computation, many-body physics, which he'll tell about here. So who is he? Adam is a JILA fellow. So if you don't know, JILA is this wonderful atomic physics laboratory that's joined between University of Colorado Boulder and NIST Boulder. And so Adam is a fellow of JILA and also an associate professor at the University of Colorado. Before that, he was a postdoc with Marcus Greiner at Harvard. Did his PhD at JILA, so I guess it's a homecoming. Couldn't get enough. With Cindy Regal, and did his bachelor's with David Hall at Amherst. So there are too many prizes to tell you all about them, but I will tell you about his miracle year of 2023, which is this year's not over yet, where he has won some really great prizes. So from the Air Force, the Young Investigator Award, the APS Robbie Prize, which is the top prize for AMO basically, which is fantastic, and also this New Horizons Physics Prize. He shared that this year. Before that, ONR's Young Investigator Award, and he won the Daymont Thesis Prize after his PhD. So I could go on, but you didn't come here for me. So I will turn it over to Adam, who will tell us about programmable control of indistinguishable particles, from qubits to clocks to many-body physics.
Does this sound good? Good back there? Okay. Ben, thanks so much for the introduction. It's been a pleasure being here, and I look forward to more conversations tomorrow as well. Let's see if this is a good spot. Is this actually showing up well here? Yeah. Can you see this right? All right, good. So as Ben said, I'll be telling you about work from my group over the past several years at JILA, sort of broadly in the area of control of indistinguishable particles and applications of that control to quantum information processing, clocks, and many-body physics. So the work that I do, and many groups here do, falls broadly into the category of quantum information science. So this is represented by tasks such as quantum communication, simulation, and computing, and, as well as metrology, all of which share the property that they're seeking to use aspects of quantum mechanics, like superposition and entanglement, to do things that are less possible with just purely classical resources alone, if not impossible. And there are many ways in which these enhancements from quantum mechanics arise, but one area is with speed-ups. Basically, something about using quantum mechanical resources makes it possible to do some particular task faster. And so let me walk through two examples of that. So one example is in computing, and I think many perhaps in the audience are aware of some of these. And a particular problem of interest in computing is factoring. And the reason we care about factoring is that its hardness actually underlies the security of many important networks and computer software databases, sort of many different things. And this is based, of course, in the algorithm of RSA. And so this problem of factoring, one can ask the question, how quickly can one do it on a classical system? So this is a picture of a drawing of something random on the internet. If I put an analogous picture inside of this box, I would probably get in trouble with someone, if not someone in the audience. So instead I'll put a picture of Peter Shor, because we don't know what this hardware will look like. Peter Shor is the guy who's responsible for the quantum algorithm that allows for factoring. And in particular, what he showed was that if you ask the question, how quickly can you factor on a classical computer, well, he didn't show this, but it's well known that this is, they're better and better algorithms, but this is roughly exponential. But on the quantum side, this can be done in polynomial time. And so you can ask the question in practice in real units of time, how quickly can one factor, say, a 2048 RSA key, which is a question that many defense agencies around the world are interested in. And the runtime for a classical system is very unrealistic. And again, this is the reason why these systems are secure. But on the other side, in the quantum mechanical system, depending on whom you speak to and whether or not they're part of a company, this can take 8 hours to a day. And so what this is saying that it takes less time to do factoring on the quantum computer compared to the classical computer. Okay, so that's a well-known example. Another one that's also quite important is in the context of metrology. So in many instances, including ones here at Stanford, one is interested in doing sensing, relying on, say, sensing a magnetic field based on the frequency of some transition in an atom or an artificial atom or an electron. And so one can ask the question, how well can you do this? So if I have, say, a product state of many spins, and I sort of produce this sample many times, and I measure and do spectroscopy on it, the precision with which you can measure this magnetic field here is proportional to 1 over the square root of the number of particles. This is just from shot noise on the sample and the fact that we get discrete outcomes when we measure the spin, just up or down. By contrast, if I had an entangled state, so a superposition, for instance, of all particles up plus all particles down, then the amount of precision that one finds is actually 1 over n. So that means that if you're doing many measurements on this sample, you could have to do fewer of them on the entangled state case compared to the unentangled state case. And that means it'll take less time to arrive at the same precision. So again, we find the situation where it takes less time to, in this case, measure with a given precision. So a natural question to ask is sort of how do we get there? How do we get to a situation experimentally or in an applied sense where these sorts of speedups are available to us? This often, at least sort of so far, begins with well-controlled single quantum objects. So instead of having some large ensemble where I'm controlling it in a coarse way, often what one does, though not always, people will individually control the particles or quanta of interest. And so there are many examples of this, of so-called quantum objects, say trapped ions, of photons, superconducting qubits, NV centers and neutral atoms, and this list, of course, goes on. And remarkably, even in this limit of just having a few or a single quantum object, there have been remarkable applications. So for instance, optical atomic clocks. These are some of the most precise sensors that are available for time and frequencies. And also for the recent loopholes-free Bell tests, here too, having just control of actually a couple NV centers was essential to the work that they were doing, as well as photons. I'd be remiss if I didn't point out that the science that was enabled by having this kind of control has been recognized with Nobel Prizes. So in 2012, Dave Wineland, when he was at NIST, and Serge Haroche in France were recognized for their groundbreaking work in measuring and manipulation of individual quantum systems, so this theme that I was just talking about. And actually, very recently in 2022, these folks here were recognized for their work in generating entangled photon pairs, so having a small number of photons that are used to, for instance, show violations of Bell inequalities. So those are examples of applications in this sort of few particle limit which have been extremely impactful, but of course there are many applications and some which are some of the most impactful that are possible using quantum mechanical resources, which don't want to operate with a few objects, but in fact many of them. And so a natural question to ask is, how do you get there? And one path to doing this, which sort of follows from these themes that I've already been discussing, is you build complexity from well-controlled individual qubits or particles. So basically, once I have a couple, I sort of add more and more, and I ask the question, as I do that, can I maintain control of the system as I build up or assemble the system? So there have been many platforms these days that have really been pushing in this direction, ranging from superconducting qubits. This is a picture from the Google experiment. Trapped ion systems. This is a picture from Rainer Blatt's experiments in Innsbruck. And also these two platforms rather are using neutral atoms. And so these include quantum gas microscopes and optical tweezer arrays. And in this talk, I'll actually discuss both of these platforms at a certain point. But for a lot of what I do, again, I focus on these neutral atoms here. But I'm going to start from the perspective of these optical tweezer arrays and how they've sort of impacted the field, what's possible with them, and sort of the history over the past really 2 decades now. And so to give you just a quick overview of what I mean by this platform and sort of give you a context for some of the pictures that I'll show, the work and sort of much of what my lab does, sort of if you were to walk into the lab and like open one of the panels and look in, you'd see like a lot of stuff that would obscure this, but if you really like, you know, peered in, you would see this eventually. Well, not this, but you would see this. And so there's a microscope. This microscope we shine light into that we take very good care to prepare in a diffraction limited way. That light is focused down by this microscope inside of an ultra high vacuum chamber. So this window here is meant to show the window into that vacuum chamber. And at the focus made by this microscope, which we call the optical tweezer, we can trap individual neutral atoms just by virtue of the interaction between the light field and the atoms. Importantly, this same microscope that we use to trap the atoms, we can also use to collect fluorescence from those trapped atoms and form images like these in sort of standard biological setups where you do fluorescence microscopy. And so this is a picture here from early on in my group where we trapped a 4x4 array of single strontium atoms. And this sort of overall architecture was based off pioneering work in France in the Grandier group, Philippe Grandier's group. Okay, so the applications of this technology over the past really like 15 years has been amazing. Ranging from few to many body physics of all different kinds of many body physics, ranging from itinerant systems to also quantum magnetism to even topological physics. They have been used both in an academic context, in a federal context, like in federal labs, and actually also now in the private sector for quantum computing. Something that my group has been focusing on is using them for metrology, and in particular time and frequency metrology. And finally, I like to highlight this really interesting work from the CUA in Cambridge, where they use the control afforded by tweezers to bring atoms close to nanophotonic devices. So you can, for instance, map quantum states stored into an atom onto propagating degrees of freedom like a photon. And the control afforded by tweezers really makes this kind of setup possible. So a lot of the work over the sort of, mostly in the slides or the pictures I was just showing you, focused on alkali atoms. These are atoms with a single electron in their valence shell. This is sort of a theme of AMO physics that people often start with these alkali atoms just because they're a lot easier to cool with lasers. But a thrust over the past 6 years or so has really been to expand this tweezer tool set to more complex systems. So this is represented by, for instance, trapping molecules in tweezers, trapping multiple different species in the same location, like a pair of different tweezer arrays. So this is a picture from Hannes Bernian's group at U Chicago. And then finally also work that my group has been doing, and also Manuel Andres' group at Caltech and Jeff Thompson's group at Princeton, where we all sort of set about in 2018 showing alkaline earth atoms in tweezers. And so one theme of this talk will be telling you about how this marriage of alkaline earth atoms with the control of tweezer systems can really open up new directions. And I'll highlight as well that while we sort of began this, there are now like a terrifying number of groups also doing this. Okay, so jumping right into it, my group at Gilla sort of has this primary theme of combining the control of tweezer systems and actually also quantum gas microscope systems with new particles and actually also new technologies. So for instance, we've been looking at, again, the sort of quantum science that's possible with alkaline earth atom arrays, and this is allowed for studies that I'll touch on probably all of today, but we'll see where I get in my talk. So I won't even define these actually because I'm going to come back to them. But another direction that I won't have time to talk about, but I wanted to mention given some of the audience, is that one thing that I've been working on in collaboration with Cindy Riegel at Gilla is developing tools for having high optical access cryogenic systems for trapping atoms in a cryogenic environment. And there are many reasons you might want to do this. So for instance, you might care about the vacuum lifetime, basically using cryopumping to get to very, very low background pressures. And this is a picture here from one of these experiments in which we've trapped an array of rubidium atoms in tweezers, and they actually stick around in these traps for more than 2,500 seconds using the cryopumping. And so this is a very long time scale compared to most room temperature apparatuses. This system is also optimized to control the black body environment as well. So for applications in optical atomic clocks and also quantum computing, sort of having this set of control can be quite impactful and has sort of been a thrust of our recent work. I'll just point out as well that actually it turns out that getting to low temperature Fermi-Hubbard systems can also be impacted by this technology and is a key thrust of our work as well. Okay, so with that, I'm going to jump right into the talk. So my goal here is I want to give a sense of the technology in our lab, since this is a colloquium that's both applied physics and fundamental physics, and then talk about how we use those tools for various directions in my group. Okay, so this picture here is a picture of an array of about a bit over 250 strontium atoms. And what's interesting is that this picture here, of course, after we image them, they're a lot hotter, but just before we image them, they're actually at a temperature of about 100 nanokelvin. And more importantly, what we've done here is that each of these individual atoms is sitting in a little harmonic oscillator trap, and it's initialized we've initialized these atoms in the motional ground state of those traps. So we've really removed all of the entropy associated with the atom's motion. And furthermore, even though we're starting with a fairly complicated atom, so for instance, strontium-88, and I should say, there are even more complicated atoms that people are able to control these days, like in Ben's lab, Ben Love's lab. One can gain high fidelity control of this internal space, for instance, to create well-defined quantum states in the internal degrees of freedom of the atom, where we've, say, picked two states to be our 0 and 1 in a qubit. And so the question is basically, and what I'll be talking about now is sort of what is the process by which we start with, say, these chunks of ytterbium or strontium at 300 Kelvin, and then arrive at a situation like this. The fact that modern technology even makes this possible is somewhat remarkable. Okay, so this process begins as follows. So we have an optical tweezer here. It's overlapped with an atomic beam made by an AO-sense source, which I highlight because I'm at Stanford, and maybe even Mark is listening to this talk. I don't see him here. Sometimes we actually even call our AO-sense source Mark. So we load a laser-cooled cloud from this atomic source. And then we laser cool the atoms from this cloud into our optical tweezer trap. And when we do this, there's something that arises called light-assisted collisions. I don't really want to dive into the physics of this, but the key point is that after this process, you end up with either 1 atom or 0 atoms, but never more than 1 atom. And this is a stochastic process, so it's always random on each run, whether or not we have an atom in each trap. Okay. So one thing that I want to highlight as well is that for neutral atoms experiments arriving at conditions like this is done in a fairly fast way compared to other manners that one might arrive at a system like this, for instance, using evaporative cooling. Okay. So in terms of the optics side, the typical core ingredients of our experiments look as follows. So we'll use a pair of acousto-optic deflectors. These are driven with custom electronics that we've developed at Gilla. And the point is that by tailoring the RF signal that we put into these AODs, we can tune the angle and power in a diffracted beam. And furthermore, that by putting multiple RF tones in, we can make multiple traps. And that's what you're showing here. So these multiple angles coming out of the AODs are turned by this lens into multiple different traps inside of our vacuum system. So this is nice. This gives you real-time control of the tweezers. Another thing that one can do is use a spatial light modulator, where you're actually gaining full control of the wavefront of the light, and the objective takes a Fourier transform of that field. So this is nice because you gain truly arbitrary control of the field. So for instance, you can make these different arrangements of atoms. You can even make Gilla, although it doesn't really have any scientific value, like using that. And you can even imagine going to three-dimensional systems. So this is a video where we've gone, we're sort of scanning in the z direction of our imaging system and finding that there are multiple foci at which we can trap atoms. So this is like a pair of layers that could, for instance, be coupled via interactions. Okay, so the next step here is, we figured out a way to trap the atoms, but then how do we detect them? Unlike, say, trapped ion experiments, what we have here is a different situation where these traps are relatively shallow. So the energy scale for the trapping is about 10 megahertz, so say like half a millikelvin. But in order to detect the atoms, we need to scatter many photons. And so you can already see that if a photon scattering is about 1 kilohertz, and I have to scatter about 1,000 photons to see the atom, you're probably going to be in trouble if this is your trap depth. And so the trick that many people use is to simultaneously detect photons, say from one transition, while laser cooling on another transition. And this allows you to remove heating that arises from these recoils of photons that you're trying to detect in order to see the atom. And so this process works very well. So this is a picture of a histogram of photon counts on a particular pixel in our camera. This is a background peak when we don't have an atom, and this is the peak that we observe when there is an atom in the trap. And this dashed line here just allows us to discriminate with very high fidelity whether or not we're trapping an atom. When this is all put together, we have something that looks like this. This is a real-time video of an experiment running. This gives you a sense of the time scale of these experiments. Furthermore, this point that I was highlighting, that there is entropy associated with the loading process, is quite clear here. Sort of on every single picture frame, you see that there's a different loading arrangement of atoms in the trap. And so this actually was a problem for a long time, and something that people thought about how to address. And then there was this pioneering work in 2016, both in Antoine Brouillas's group in France and also Misha Lukin's group at Harvard, where it was shown that what you can do is see where the atoms are. So for instance, in 2D, you might see an array that looks like this or looks like this and so on. And then you use a moving tweezer array using these AODs that I was just telling you about to rearrange the atoms into target patterns of interest. So for instance, you can go from here to the square array. You can prepare a heart array if you're interested in doing so. And actually, in 2017, I believe, they actually even rearranged an Eiffel Tower, which, like the Gilla rearrangement, has basically no scientific value, but it's great for colloquia like these. Okay. So that's the main things I wanted to say about the sort of tools in our labs and in my labs and how they sort of underlie the work, the physics that I'll now discuss. Maybe if there are any questions, now is a natural time to answer on the sort of technical side. Okay, if not, I'll keep going here. Okay, so I mentioned that a key theme of our work is really in this area of alkaline earth atoms. And so what that means is I need to give you a sense for what the atomic structure of an alkaline earth atom looks like, and furthermore, why that structure is actually enabling of the physics that we look at. And so this whole section of the talk is sort of developing the complexity, increasing the complexity of the number of states that we use inside of this atom. But at first, I'm just going to sort of tell you about all the level structure. So there's this singlet S0 ground state, which is a 2-electron paired state because these alkaline earth atoms have 2 electrons in their valence shell. There's a triplet P0 metastable state, and often one talks about how these two levels here can be connected with light on what's called the clock transition, and why it's called the clock transition I'll explain in a bit here. There's another transition called, which we often call the cooling transition, and it's connected to this triplet P1 state, which has the property that it's actually fairly narrow compared to, say, what arises in alkali atoms, but it's not quite as long-lived as this metastable triplet P0 state, which, depending on what atom you're working with, can exist for hundreds of seconds, whereas for this triplet P1 state, it's sort of the lowest, the lowest lifetimes, or sorry, the longest lifetimes that you can have are sort of on the order of 20 microseconds for at least the atoms that I'll be talking about. There's this triplet P2 state, which my group doesn't work with, but I think some people are thinking about using. And there's also this broad transition here from the singlet S0 ground state to the singlet P1 state, which is often used for detection of atoms very quickly, because you can scatter many photons quickly off this transition due to the fact that it's broad. Finally, another level of interest, which has been used, or a sequence of levels of interest that have been used for by many groups, is this Rydberg series here, and I'll explain why this is useful and what's key about it. But maybe just to say up front, the key point is that these levels here correspond to very highly excited states of the atom, where if I have 2 atoms next to each other that are in these Rydberg states, they experience a strong interaction as a result of the electrons being largely deconfined with respect to the core of the atom. So these electrons can repel each other and feel that they're there, and therefore allow for interactions. Okay, so this first part of this section of the talk is really going to focus on these transitions here and how we use them. And the big picture physics that we're interested in sort of boils down to something that was emerging from, at the time of my, end of my postdoc, a lot of people were thinking about. And it's this question of how to combine scalability with neutral atom systems with microscopic control and detection, and furthermore to do this in a way that allows for a lot of different physics. To give you a sense of sort of why this question was on people's minds, so there's this quantum gas microscope platform that I didn't quite describe earlier in my talk, so let me give you take a second to explain it. So there are these platforms here, the quantum gas microscopes, and the idea is that by trapping a large sample of neutral atoms in standing waves of light, these atoms actually exhibit itinerant physics. They can tunnel inside of this lattice in a way that's very similar to electrons hopping in a solid. And furthermore, if there are two atoms on the same site, they can actually experience a strong interaction. So this allows for the creation of Hubbard models. And importantly, the microscope that's used in these systems can allow for single site resolution of atoms in this lattice. This allows for essentially single atom and single site resolved snapshots of a many-body wave function. On the flip side, there are these tweezer arrays that I've been talking about. And typically in these situations, you have single atoms that are trapped in the tweezers. They're not hopping between them, but they can exhibit long-range interactions in a very tunable way. So I can arrange the atoms sort of in this arbitrary way that I was showing you in previous slides. So you have this level of programmability that has allowed for a number of different studies of, for instance, quantum magnetism, as I said. And so one question that we were thinking about is whether you might be able to combine the programmability, the control that you have in these tweezer array systems, as well as the actually very fast cycle time that they have, with the physics that's observed in these quantum gas microscopes, namely the physics of Hubbard models and itinerants. So as I said, there have been a lot of people thinking about this and different demonstrations in this area. The sort of approach that we took was to just like the really brute force approach of basically let's just combine these two technologies together. And so what I mean here is that we have optics that produce a 2D lattice of atoms. On the right here is a picture, an average picture of atoms loaded into this lattice potential. So this gives you a sense of the number of sites at which we can trap and image individual atoms. So this gives us both scalable detection and control of these atoms, but at the same time, by having the tweezers co-located with these atoms, or with this lattice potential rather, we have the single particle control that I've already been telling you about from tweezers. Okay, so using these tools, let me walk through sort of what an experimental sequence looks like. So we'd load an array of atoms. This is supposed to be like a 3D projection of an array of atoms loaded into tweezers. And the goal is how do we get to a low entropy system, both in terms of the positions of the atoms, I'm referring to that as density, and also their motion on each of the individual sites that they'll eventually be trapped at. And so what we do is we rearrange the atoms into sort of arbitrary configurations. So this is rearranging the CU logo. And then, of course, we can do this for many other configurations of interest. And this is the first time that people have really done this kind of rearrangement using tweezers in a lattice potential, and in particular at these length scales. So the lattice sites are, adjacent lattice sites here are separated by 575 nanometers. So this gives you a sense of the level of control that we have using tweezers. So this is an array of atoms on adjacent sites. This is an array of atoms on every other site. This is strontium-88 pointing at a strontium-88 atom. Sort of get the themes here. It's sort of playing with this essentially. But of course, you want to use it for physics as well. And so this gives us control of the entropy from the arrangement or the density of the atoms. We also, as I said, care about the motion, and here's where this narrow line cooling transition that I mentioned comes in. Importantly, there are well-established techniques for laser cooling that rely on being in a regime where the line width of the transition is much less than the oscillator frequency. In our case, this gamma is about 7 kilohertz, while omega is a bit over 100 kilohertz. So this means that we can cool the average occupation of the atoms, this is this n bar here, to a very, very low number. In practice, after we cool, we get spectra like these. These are known as sideband spectra. For the experts in the room, they'll sort of know how to interpret this. But the key point is that after we take such spectra, we're able to know that we have a 3D ground state fraction, meaning the motion in all 3 dimensions of our trap are controlled at the 95% level. We've initialized the atom with 95% probability in the 3-dimensional ground state. Okay, and then once we've done that, we can sort of explore the physics of interest in this ground state manifold of the lattice. So let me take a second then to explain like what kind of physics is available to us in this lattice system, some of which I've already touched on, but just to review sort of in more detail what all of the symbols in the previous slide meant. So we have this Hubbard model here, which describes both the hopping of the atoms on the lattice. This is a kinetic energy term that causes the atoms to delocalize in the lattice. These are tunneling operators here. As well as contact interactions, which exact an energy penalty whenever you have more than one particle on a site. And so this actually competes with this delocalization term because it serves to penalize having multiple atoms on the same site. We work in this particular experiment with strontium-88, which has the property that its scattering length, which parameterizes how readily these atoms collide, is actually very small compared to most atoms. So it's about 2 Bohr for those who are technically interested. But the key point is that basically the result of that is that this contact interaction term is largely negligible. You can just sort of not worry about it for this physics. And therefore we arrive at a situation where the atoms just delocalize in this lattice, and this follows the physics of actually a beam splitter network in the sense that each time an atom tunnels or stays where it started is equivalent to a photon going on the beam splitter and either being reflected, that would be a case of it hopping, or transmitted, that's like staying in the same mode that it began in. And I sort of wanted to seed that intuition as I move forward here. Okay, so we can look at this from sort of by growing the complexity of the system. So if I have a single atom here, if I initialize it at the center of the lattice, and then I run many times, and just so this is a video of running the experiment many times, and this is the average distribution of that single atom. What you find is the sort of telltale sign of a 2D quantum walk. And what you see here are interference fringes in the density distribution of the wave function associated with all the multi-particle paths that interfere on the lattice. So that's one particle, but you can also think about 2 particles. And so in this situation, again, these are non-interacting bosonic atoms, and we can prepare them on neighboring sites and then let them tunnel in this lattice. So this 1 millisecond here is about on the order of a tunneling time. And you see some density distribution like this. But remember, these are non-interacting bosonic atoms, so actually the density doesn't tell us that much, which is interesting. But in fact, if you consider the correlations on the lattice, then something very interesting emerges. So if you have these 2 atoms on neighboring sites, you can ask the question, how likely is it that I end up after I tunnel in that same configuration? And what, if you sort of subscribe to this intuition I was telling you earlier, that corresponds to the case of having 2 photons on a beam splitter. And there's the case where both photons are transmitted by the beam splitter, and the case in which they're both reflected. And if you go through the math, what you find is that these have equal and opposite quantum amplitude, and therefore cancel. And what that means is that you observe something known as Hong-Ou-Mandel interference, and in particular something known as the Hong-Ou-Mandel dip. So this is a plot here of the coincidence counts, that is the likelihood to get this configuration, as a function of the position of this beam splitter here, which really tells you about how indistinguishable the photons are when they arrive on this beam splitter. We observe something very analogous to this in our system, although our x-axis means something slightly different. And what we can tell from these plots is that we're able to prepare the atoms with actually, we can sort of detect their indistinguishability and their purity with better precision than the spectroscopic signature I was telling you about. And in particular, we have 99.5% indistinguishability of the particles. Okay, so I just sort of told this story that we have this method for...
So can you say what that means? What does 0.5% non-indistinguishability mean?
Yeah, so really what this means here is basically that I have these 2, I have a density matrix that describes the quantum state of each of these atoms. These 2 density matrices are exactly the same up to the 0.5% level, actually the square root of the 0.5% level, because it's an overlap that we're looking at. Does that make sense? All right. In other words, it's a purity. It's a measure of the purity of the wave function. Okay, so now we can sort of turn this to 11 and sort of add more and more particles. And so I want to highlight sort of why, even in this situation where you have no interactions, this might be an interesting thing to look at. So, and in particular, you can ask the question, if I start with this initial configuration here, this is an arbitrary one that I'm drawing, actually that Malta is drawing, and I have some other configuration here, this final one, And then there's some single particle unitary that describes how the quantum amplitude for a particle at site J to end up at site K. What is the likelihood that I go from this initial configuration to this final one? And so, to do this calculation, what you say is, okay, well, I need to consider all of the many particle paths that take me from this configuration to this one. So there's this set of paths, but of course there's also this set of paths and this set of paths, and in fact, an exponential number of such paths. And this actually corresponds to the problem of calculating the permanent of a matrix. And this fact underlied a pretty influential theory result from Scott Aronson and Alex Arkhipov that showed that basically if you consider the dynamics of photons on a beam splitter network, provided you're able to satisfy certain assumptions, that is a problem which is classically very hard to calculate. But what I've been telling you so far is that this beam splitter network that we're able to produce in the lattice is exactly the physics that we would need for this. And so let me point out that this has also motivated many experiments in photonics. So this is a picture from Jiawei Pan's group where they've made this just enormous beam splitter network. I think when Amir saw me give a talk at one point, he pointed out that this would be in every single grant proposal in integrated photonics, sort of after the time that this photo was published. And so this has been used for Fock state sampling, so starting with individual photons for 14 photons on 60 modes, and also with Gaussian squeeze states for 70 states and 100 modes. Okay, so we've now sort of explored this situation, sort of adding more and more particles, and the sort of natural question to ask is, what do you look at in this situation that's computationally difficult by construction in order to know whether or not what you're doing is what you think you're doing? So there are a couple ways of doing this. So one is looking at bunching. This is the likelihood for the particles to end up on the same output mode as a function of particle number. And there's this interesting trend that for indistinguishable particles, which we prepare, we see a trend like this, which is actually n factorial higher than what we expect for what we find for distinguishable particles, which we can actually simulate in our experiment. And just to give you a sense of how sensitive the signal is, this dashed line here corresponds to when we have just one of the particles distinguishable from the rest. So this signature is sensitive to the indistinguishability of the atoms as we add more and more of them. However, you can see that the incidence of this observable is getting smaller and smaller. So this isn't a very scalable way of trying to actually detect whether or not we're sort of witnessing multi-particle interference in the experiment. So there are these sequence of papers in 2016 and also 2021 that offered a much more sort of coarse-grained way of looking at interference on the lattice. I can answer questions about this at the end, but the basic idea is looking at a form of generalized bunching that arises as you randomize over the modes that you sample from. And if we study this witness parameter, which we call pk prime here, as a function of adding more particles, what we find is that the data in the circles here corresponds to these our actual indistinguishable experiments. This blue line here at the top corresponds to the case where we're using the best known sampling algorithm, the sort of Clifford and Clifford algorithm. We see good agreement with our data. And then if we simulate the effect of adding more and more temperature, so which allows the atoms to be distinguished, we find that we converge on experiments where we deliberately make the particles distinguishable. So this is really showing that not only is the experiment behaving as we expect, but furthermore, this metric is also behaving as we expect as we add distinguishability to the experiment. And we've actually turned this up all the way to 180 atoms where we sort of sample from these large distributions and look at how these observables are manifest in the experiment. And so this corresponds to actually the largest instantiation of boson sampling with bosons. But I should say that there are really important assumptions that actually our experiment, and in fact none of the experiments fully satisfy to sort of reach the hardness claims of Aronson's work. But nevertheless, we have a lot of reason to believe that we're in a regime where we just really can't push in the calculations further. Okay, so with that, let me just highlight that this work was with non-interacting particles, but what we're really pushing for now is adding interactions to the system, which is nice for us because we can achieve that just by changing the isotope of strontium that we work with. And so just to give you a qualitative sense of how this looks, if we rearrange to a situation like this and we look at strontium-88, we see an average distribution of the particles that looks like this after expansion of the atoms on the lattice. Whereas if they're strongly interacting, that's what we get with this strontium-86 atom, In fact, the atoms, because they're colliding with one another as they sort of expand, they're confined in the lattice and their transport is frustrated. So you're in this situation here where the atoms expand and their dynamics is totally different. I'll highlight as well, just because I'm here and John and Dave are at Stanford now, there are ways of actually also sort of assembling superfluid systems from individual single atoms. And this is a very interesting thing because you normally think of superfluids as having uncertain particle number, but in fact, these situations that we're working with have very well defined particle number. So there's a lot of interesting quantum optics to look at in this kind of system. Okay, so that was using these two transitions here. Let me add another transition, which is this transition called the clock transition. And so these next couple slides are sort of explaining why we call this the clock transition. So the reason we call it the clock transition is because this transition is used for optical atomic clocks, which are devices which use a laser, which you can think of as just an oscillator. And this laser is locked to an atomic transition. And this atomic transition is nice because it allows for an absolute reference on the passage of time. And a key metric for how well you can do this is the stability. This stability here tells you about the precision between the frequency of the laser and the atoms as a function of averaging time tau. And it depends on the frequency of this transition, this omega EG, the number of particles that we have, and the coherence time, that is how long you coherently interrogate the atoms with this laser. And so the fact that that the stability here can actually be so good if you're working with optical transitions, which are, again, this precision here goes like 1 over this frequency, so optical transitions are great, has motivated a ton of development. So on the laser development side, this has motivated work, for instance, at Gilla and also in Germany, preparing lasers that have sub 10 millihertz line width using silicon crystal cavities for stabilizing the laser. But at the same time, it's also motivated tons of work on the atomic physics side. So for instance, what we care about is having a long coherence time, like basically how long you can store a phase in the atoms, and doing so at these optical frequencies. And furthermore, having many atoms, that is dialing up this n here as much as possible. And so the leading platforms for doing this kind of physics are and have been trapped ion systems, which operate with, say, a single ion, so this aluminum ion here, and then use this other ion as a way of reading out the state of this aluminum ion. And these systems are remarkable. So they can, for instance, measure a millihertz frequency on a petahertz transition. So that is a fractional accuracy below 10 to the minus 18. On the lattice clocks, you sort of operate in a different limit where you don't quite have the control of these trapped ion systems, but you have many, many atoms. That means you can get precision very quickly. So in these experiments here from Shimon Kokowitz's group, he's now at Berkeley, and Jun Yi's experiments at Gilla, they were able to resolve the gravitational redshift on length scales below a centimeter and actually even below a millimeter. So that really tells you just sort of how remarkably sensitive these devices are for timekeeping. Okay, so in our work, one of the things we set about asking was whether or not there might be a platform that sits between these two that combines the control that you have in these trapped ion systems with the sort of scalability that you have in these lattice clocks. And so in 2019 and 2020, working with these folks here and actually some Stanford alum, we first benchmarked this idea. So we looked at the idea of a tweezer clock where you have an array of single atoms. And in the end, what we found is that we could get up to about 160 atoms, although I don't think this is the end of what one can do. And actually, by having this number of atoms and being able to read out the atoms individually, we're able to see that the atomic coherence time was about 20 seconds. So what this means is that even though these dipoles in the atoms are flipping around at hundreds of terahertz frequencies, they're staying in phase for 20 seconds. So this is an extremely high quality factor for an oscillator, which is why they're such good timekeepers. We furthermore were able to see that at a single particle level, we had coherence of about 50 seconds. And so at the time of this work, these were actually the longest coherence times that had been observed in an optical atomic clock. And putting this all together, we could get to stabilities of 5 times 10 to the minus 17. So in other words, at 1 second of averaging, we could keep track of time at 5 times 10 to the minus 17 in fractional precision, comparing the frequency of part of our ensemble to the other part of the ensemble. Okay. So I'm just going to rush a little bit here in the interest of time, but I think I'm good. So that was the work that we were doing adding this clock transition. But sticking in this area of metrology, we can actually add this Rydberg transition here. And I mentioned this earlier, but just to remind you, the idea here is that if I have atoms near one another that are excited to these Rydberg levels, shown in red here, then they experience a strong van der Waals or even dipole-dipole interaction, just because when the atoms are excited in this way, the electron orbits are so loosely bound to the atom that the electron orbits actually can feel one another when the atoms are close enough together. And so this is a way of precisely engineering interactions into your system. And what this allows one to do in particular is start with a stability that looks like this. This is this expression I was showing you earlier. And actually realize a situation where the stability of your system can be improved not just using the number of atoms or the coherence time, but actually the amount of entanglement that you add to the system. There's a lot of sort of formal work that goes into this idea, but basically it's captured by this parameter here, which is known as the squeezing parameter, C. And so importantly, when you have the right kind of entanglement, this number can be less than 1. And one thing that I like to point out when I give this talk is that this is this idea of using entanglement to improve the precision of a measurement is actually like a proven demonstration of where a quantum mechanical system is allowing for an enhancement over what's possible with just classical resources. So for instance, at LIGO, they're using squeezed light. This green line here corresponds to the noise floor of the system when squeezed light is injected into their interferometer. The black is what they had before adding the squeezing. This has been used for bounds on axion detection in a collaboration at Gilla and Yale and actually a number of groups. And actually, it has also been explored in applications for entangled optical atomic clocks. And notably, von Vuletich in 2020 showed squeezing on an optical atomic clock using interactions with a cavity. And so there are many different ways that you might prepare an entangled clock. And it's worth pointing out that these different ways of doing it have different merits and benefits. So for instance, there's this idea of squeezing, where you have quantum noise in the direction of a collective spin vector. And by allowing for the atoms to interact, you can actually shear this distribution. So for instance, in Monica Schleiersmith's group and also Mark Kasovich's group, these sorts of states are produced. And the idea is that along one of the axes of this shear distribution, there is a reduced noise that you can use to actually do more precise sensing, because the quantum projection noise has been reduced in that direction. And so what this does is effectively improve the effective number of particles that you have. You're not actually changing the number of particles, but you're changing the shot noise associated with that number of particles. Another case is you could have a GHZ state. So now, instead of having a superposition or a product state of a superposition of E plus G, you have this GHZ state of all up plus all down. And what that means is that because of this larger energy separation between the bottom of this Bloch sphere and the top, you accrue a phase much more quickly. And so effectively, you've actually increased the frequency of the transition that you're probing, and thereby improved the precision of your clock. So that's another kind of entangled state. And then finally, there are these very, frankly, beautiful ideas of using quantum circuits to both encode a state and then decode a state that was subject to some signal of interest. So this is this encoding and then decoding step, and in the middle here is some detection sequence. And what this can do is allow for basically optimization of all these parameters, plus actually increase the dynamic range of your sensor. So this is a very sort of interesting suite of ideas that came out of the Zoller group, and actually some other papers before that too. Okay, so the platform that we've produced to sort of target really all of these different ideas is this programmable strontium clock platform, where we have, on the one hand, high fidelity control of the clock transition. So we've spent a lot of time trying to get the atomic physics down so that we can really control with high fidelity Rabi oscillations on the clock transition in this two-level system. So basically trying to treat this optical frequency qubit like a qubit. On the other hand, if we just consider this excited state to this Rydberg state here, what we have is a situation where there's an interaction potential that we can very controllably add to the experiment. It looks like this here. These circles here are actually data from the experiment that give you a sense of the shape of the interaction potential that we produce, and also its scale. So it's about 100 kilohertz, and it extends over about 5 lattice sites. and then drops off. If you put this control on the clock transition and if you put in this control on the clock transition and combine it with this Rydberg physics, what you're able to do is prepare a very controllable Ising model. And actually, you can even add a transverse field on this clock transition too. And so with this set of tools, we can sort of explore two different directions. So we can look at the analog dynamics of some many-body system under the influence of some many-body Hamiltonian. Or you can rearrange the atoms such that they're really only talking to one other partner, and sort of consider this you can think of this as sort of an ensemble of qubit pairs, but importantly, we could rearrange them in real time if we wish and actually encode a circuit. And so the first thing that we did using this platform, which was recent work, was use these Rydberg interactions to do spin squeezing. So this is inspired by this seminal work from Thomas Pohl, where they showed that under the influence of this interaction potential, this is another way of writing out this Ising interaction that I was showing you before, that there is squeezing, this C parameter that I was telling you about, and focusing on this green here, which corresponds to two-dimensional systems, you can have squeezing that's pretty substantial in the presence of these dynamics. And so we can look at that as follows. So we prepare two arrays of atoms in our sample. So we have an array here, an array here. And importantly, the interactions between the atoms extend within these samples, but not between them. So we have sort of two copies of a many-body state. We apply a pi/2 pulse to prepare a coherent state. And then in the presence of this Rydberg Hamiltonian, we actually observe this shearing that arises from the interactions. And then we inject this into a Ramsey sequence so that we can actually first orient the squeezed ellipse in such a way that we have maximal sensitivity, and then accrue a phase which we can measure more precisely as a result of the reduction in quantum noise along this axis. And then what we do at the end is we read out the sample and compare the frequency of this ensemble compared to this ensemble. So this is a differential frequency measurement that allows us to reject common mode noise from our laser. So when we do this, what we find is that as a function of phase angle, which is the orientation of this ellipse, we see variance reduction, so that falls below the quantum projection noise of a coherent state, which we can both calculate theoretically with this solid line or actually measure directly with coherent states. Those are the squares. And importantly, this variance reduction is, while it's increased or reduced here, it's actually, we have anti-squeezing at this phase angle. And so we can look at the microscopic correlations to see how they actually give rise to this. So for instance, when we're at this squeeze situation here, that means that we have negative correlations between the atoms, and the noise between the atoms is actually canceling in order to improve the total variance of the ensemble. And the opposite happens when we're in this anti-squeeze quadrature. You have positive correlation, so you have correlated collapse in the wave function. And then importantly, what we find is that the amount of contrast loss of our interferometer from this squeezing is actually quite minimal. And this is important because this basically tells you how much authority on a phase you can have in your interferometer, because if your spin was fully decohered, you couldn't really measure a phase. And that is not always the case, that these operations actually preserve the spin. And so what we find is that the usable squeezing, often referred to as the Wineland squeezing, gets to about 4 dB as a function of interaction time. And so we can inject this into an optical atomic clock, and we observe that indeed, if we do a stability measurement, an Allen deviation measurement, we find that for a coherent state, we have stability that sits right on the standard quantum limit, whereas for squeeze states, it falls below it. And actually, if you look at the distribution of outcomes in these frequency measurements, you can actually see the noise is actually reduced in the squeeze state quite directly. So this results in about 3.5 dB squeezing below the standard quantum limit. We can also increase the number of particles, which improves the overall stability that we get, but we actually get slightly less squeezing when we do this. And I should say, altogether, this is the first time that an optical atomic clock has directly operated below the standard quantum limit when actually operating as a clock. Okay, so I'll just close here by saying that the next steps here are sort of to look at this other side, the sort of digital side of the experiment. So we've been working on 2-qubit gates. These are plots here which show you that we can use a sequence of gate operations on the atoms to prepare the population so that they're actually in a superposition of EE plus GG. So basically, if we measure the atoms, they're always in one of these two configurations. And this plot here is known as a parity plot, and it allows us to tell for sure that we have coherence between these two configurations, and therefore benchmark the fidelity of these operations. And so we were able to get about 98.3% raw Bell state fidelity, which actually matches the state of the art for hyperfine qubits, which was recently reported, but using these optical qubits here. But we can do this for not just 2 atoms, we can go up to 3 atoms, and we see that these parity fringes speed up. We can go up to 4 atoms and still retain like fairly decent fidelities. And again, the frequency of these parity fringes gets even faster. And this idea of these fringes getting faster and faster, and therefore the slope of this getting steeper and steeper, underlies a very interesting proposal for using a sequence of GHZ states to have a Heisenberg limited optical atomic clock. Heisenberg limited means that it's the best possible that you can do using entangled states. And in fact, we've sort of recently started toying around, playing with this idea where we, in parallel, can make multiple different size GHZ states in our sample. Okay, so with that, I think I only have 2 more slides here, so I think I'll close and just say that all of the work that I've been telling you so far is focused on the strontium atom, which is this bosonic atom. This clock transition here that we've been treating as a qubit, it's great for metrology. It's actually sort of horrible for quantum information, because in order to control it at high fidelity, you need incredibly good lasers and oscillators. And that doesn't really make for like the best quantum computer. But importantly, there are spinful isotopes of alkaline earths. And in particular, there's this ytterbium-171 atom, which has a nuclear spin that is really nice for quantum computing. And so our group, and actually Jeff Thompson's group, has been exploring this atom as a vehicle for quantum computing, really leveraging all the nice features of nuclear spins to do that. So I have 2 more slides here, but I think I'm going to skip through them and just jump to the end so I can get to my acknowledgements. With that, I think I'm going to close. So this is a picture of the group here. The work that I was telling you about really focused on the strontium experiment, which was built in the beginning by Aaron Young, Matt Norcha, who's now at Atom Computing, again, as I mentioned, a Stanford alum, and Will Eckner. And then now the more recent data was taken by Alec Tsal and Nelson Darkwa Pang. And this is sort of the full team from my lab, and we have our collaborators in the Yi group and also on the cryo team. And with that, I will close. Thank you.
Questions?
Thanks for your great talk. I wanted to ask a little bit about sort of how you see the future of using entanglement for squeezing and improving on these sort of metrological applications. It usually seems like the factor of gain is like somewhere between 2 and 10, and it's a lot of work to reduce it. What sort of is the fundamental limits you see coming up to this sort of technology? Is it worth it for us younger researchers to push in this direction?
So I can't say no. Okay, so a couple things. So one, I think there's the more detailed answer that refers to just the specific work that my group has been doing, but I think there's sort of a broader answer too. So for the sort of narrower scope answer, referring to my group's work, the amount of squeezing that we actually get is limited by the range of the interactions, because we're working with this particular form of spin model, an Ising model. But in collaboration with the Ray group at Jello, we've come up with some ways of basically breaking past that limit, which would allow for more than 10 dB of squeezing. So that's not like a factor of 100 improvement, but it's still a pretty substantial improvement in the precision, given like the amount of resources that you have. Furthermore, there are ideas, these variational ideas that I was referring to for optimal sensing that give you similar levels of improvement. Sort of in a broader sense, I would say that I might sort of flip it around and say that this is sort of just a fundamental physics line of research. Like, we're learning basically how we can control the many-body physics of these systems, and also the sort of circuits that are relevant that can sort of push the frontier of what's possible doing precision sensing. And so I think by flipping it on its head, what I'd say is that we certainly don't know right now that it's not possible to push this further. And I think that's a reason to keep pushing on it.
Questions? Oh.
So at the sort of one-third part of your talk.
Okay.
You just barely mentioned, but then never came back to making your experimental platform in 3 dimensions instead of 2.
Yeah.
And of course, you know, if you're interested in many-body effects, like for example in molecules, it makes a huge difference once you break into the 3rd dimension. So I'm wondering what the opportunities are there.
Yeah, that's a great question. So I think there's sort of 2 ways, again, of answering it. So the first is that, you know, there are people actually, Nathan Shine, who's a former postdoc in the group, is thinking about actually trying to do this. The challenge here is that while, you know, I showed these images where you can prepare 3-dimensional arrays of traps using a spatial light modulator, it's a little tricky to do the detection because you have multiple image planes, all of which need to be focused onto your camera. So there's sort of the brute force way of doing this where you actually literally shift your camera and make multiple images, which is the Eiffel Tower picture basically does that. But there are also sort of interesting ideas for basically borrowing ideas from biophysics to in a single frame get multiple, sort of in a single position of your image plane, get multiple planes from your atoms. And so once you've solved that problem, you can really think about doing 3-dimensional physics in the presence of all these tools that I was just telling you about. So that's the first answer. The second answer is that there is this beautiful work very recently from Harvard that showed that you can move the atoms around in real time and encode a circuit. So I don't need to fix the atoms and do all the physics of that particular configuration. I can in fact have one configuration and then reconfigure the atoms and do a gate sequence, reconfigure the atoms and do a gate sequence. And therefore what that means is that I'm changing the connectivity of my system in a nearly arbitrary way. And so if I wanted to prepare a 3-dimensional system starting from a 2D one, I could do that in a digital fashion using these tools as well. And you could even go higher than that as well.
Another question? No? All right. Oh, wait, Leo. All right.
So, you make some beautiful pictures of the high stability between different areas in a single. How much do you think that translates to another place, or are the tweezers?
Yeah, so let me, so this is a very good question, and also let me explain for the audience what specifically Leo is asking. So what we do here is we compare the frequency of a transition, and actually more specifically what we do is we measure the phase in a Ramsey sequence differentially between one side of our ensemble, one part of our sample and the other side of our sample. And this allows us to reject noise in our laser. I think I said that point, but it's pretty important because what it means is that in this picture that I was showing you of how you'd use an optical atomic clock where a laser is locked to the atoms, that's exactly what we're not doing, right? We're actually looking at time differences within our sample, not with respect to the time being kept by the laser. And so the question is, basically, how much does the performance that I just reported translate into a true optical atomic clock that's using the laser as a timekeeper, correct? Yeah, so if everything was perfect, it would happen perfectly. But the main challenge is that the structure of the laser noise can be a huge problem. And so for instance, these ideas from that I was mentioning at the end using a sequence of GHZ states, that actually might allow us to get pretty far because what that does is it allows you to keep track of fringe slips in your Ramsey sequence, which are getting faster and faster as you have a higher and higher order GHZ state. But because you have many of them, you're able to track all those fringe slips while retaining the sensitivity of the sort of most sensitive GHZ state, namely the biggest one. So, coming back even to the first question, I would say we're still learning, but this is sort of the best that we can do right now. But I'm optimistic that we can get pretty close to this. And actually in this work, we're going to do most likely atom laser comparisons as opposed to atom-atom comparisons to really sort of make use of this dynamic range.
Okay, any last questions? No? Thank you, Evan.
Oh, thanks.
Unbelievable. What do you guys?